All right, so our first lesson was about rectangles, and we had LRAM, RRAM, and MRAM that stood for the left rectangle approximation, the right rectangle, and the midpoint approximation method. And one of the things we discussed is that those rectangles aren't really great at estimating all the time. I mean, they're decent, but couldn't things be better? And the answer is yes, things could get better. And one of the ways that they could get better is we could do trapezoids. So today we're going to talk about the trapezoid approximation method. So if I take this region right here and I want to draw in some trapezoids, I am going to partition this into 4 subintervals like so. And when I partition it, here's how you make these trapezoids, is you draw in each of your heights here at each value of the partition, and then you just connect the endpoints. So I'm going to put one thing there, I'm going to put one thing there, I'm going to put one thing here, and I'm going to put one thing there. And you're going, Mrs. Vibber, wait a minute, how are those trapezoids? Well, here's how they're trapezoids. Isn't this parallel to that? Yes. And if I were to take this guy and turn him on his side, wouldn't it look something like this? Wow, that's crooked. Wouldn't it look something like that? Isn't that a trapezoid? It's totally a trapezoid. So that's why this is called the trapezoid method, is that technically you get trapezoids that are right trapezoids. They've got 2 right angles, and they just stand on their ends. All right? So one of the things you need to remember about all this is you need to remember that if you have these trapezoids, the area of a trapezoid is h over 2 times b1 plus b2. H over 2 times b1 plus b2. And we're going to use that a whole bunch. So let's come down here and draw and use 4 trapezoids that can be used to estimate the area between the graph of this parabola and the x-axis on the interval from -1 to 3. Then estimate the area. Is this estimate over or under the real value? I am not sure. All right, so my trapezoids will start here, and then I have 1 at every unit here because I'm going from -1 to 3. And then to draw in my trapezoids, I just connect the dots. Wow, look how nicely that seems to fit the curve. What a great idea these trapezoids are. So there's my trapezoids. And now if I want to take the area, we're going to call this of trapezoid number 1. If I want to find the area of that trapezoid, trapezoid number 1, the height of the trapezoid is the width of the interval. So I have h over 2 times b1 right here and b2 right there. So h over 2 times b1 plus b2. b1 is the y value when x is -1. So that's going to be f of -1 plus f of 0. And then trapezoid number 2 is going to have the same one as my height. My first base is f of 0. My second base is f of 1. My third trapezoid is still going to be a half f of 1 plus f of 2. And then my fourth trapezoid is going to be 1/2 times f of 2 plus f of 3. Now, obviously, that looks like I'm writing a whole bunch that I don't need to write, and that's true. I do need to condense this here. So our area right here is going to be 1/2 times, I did f of -1, but I only did it once. Then I did f of 0 twice. I did f of 1 twice. I did f of 2 twice. And then I did f of 3 once. Makes sense? Because in the interior, 0, 1, and 2 are all interior bases, which means they're the b2 for one trapezoid and the b1 for another. So I have 1/2 times that stuff. I'm going to pull it up in the calculator here and say, all right, I'm doing 0.5 times f of 1. So in my y equals, I've got the equation of the graph. And I'm going to do 0.5 times vars, y vars, vars, y vars, function y1 of 1. Nope, -1. Wow, get my head together here. There we go. Plus 2 times vars y vars function y1 of 2 plus 2 times vars y vars function y of 0, because I forgot the 0 and the 1. Vars y vars function y1 of 1. If you're wondering at home, dear God, what is she doing? I went from -1 and jumped to 2 for some unknown reason, so I needed the 0 and the 1 back. And I actually need to double this 1 because I lost my 2. There we go. And then plus, finally, vars, y vars function, y1 of 3. Am I done yet? God, I hope so. There we go. Whew. All right, 10. That looks okay, I think. I'm looking back at my work here, and it looks like 10. 10 seems good to me. So my area here is 10. Is this estimate an over, an under, or what is it? Well, if I look at this, the way I've drawn it, it kind of looks under, but if you really think about where these lines would go, they'd go over the top of the parabola. So this is going to be an over approximation. Why? Well, because of how the parabola bends. If something bends like this, and I connect it with a straight line, the straight line is going to go over the top because it's what? Concave up. Who said that? It was me. A function's concavity determines whether trapezoids will yield an over or an under approximation of the area. So if you want to determine whether trapezoids are over or under, you have to look at the concavity of the function. If you want to look at L or R RAM and see if they're over or under, it's whether the function is increasing or decreasing that determines that. Okay. So if we came down here and filled in these blanks, if using R RAM to estimate the area beneath y equals e to the x, whoop, on an interval from a to b, if I'm using R RAM, it would be an over estimate, because if I drew in a right-handed rectangle, it goes over the top because why? E to the x is an increasing function. If I use trapezoids on e to the x and I drew in 2 lines and then connected them, that is also going to be an over approximation because e to the x is a concave up function. Okie dokie. All right. So now let's do a little more. Estimate the area bound between the graphs of y equals ln x, y equals 0, which is the x-axis, x equals 4, and x equals 12. All right, so y equals ln x looks like this. And it intersects at 1. And I'm finding area between 4 and 12. I'm going to use 4 intervals in the trapezoid. Is it an under or an over approximation? Well, I can tell you right now, this is going to be an under approximation because ln x is concave down. And if I think about something that's concave down, when it bends like this, if I draw 2 lines and connect them, it's underneath the curve. All right, now we actually need to do it. So if I'm going to do 4 sub-intervals, let's see, from 4 to 12 is 8 units. So these go up by 2, so 4, 6, 8, 10, 12. I'm going to connect the dots here. And since those are all equal width intervals, I'm going to have h over 2 times the first height, which is at 4, so that's going to be ln 4. Plus 2 times the second height, which is ln 6, plus 2 times the third height, plus 2 times the fourth, plus 1 times the last. All right, so let me quick get an answer here. So that's 1 times ln 4 plus 2 ln 6 plus ln 64, yay log laws, plus ln 100, yay log laws again, plus ln 12. Mrs. Bibber, where did you get 100? I use the shooting star rule just to be annoying. 10 to the second is 100. Those were all being multiplied by 1. 16.218. Remember, it's okay to truncate or round. All right, now, last but not least, this is something that hasn't come up yet. One of the things I keep talking about is that your partitions, when we've been doing it, are all equal widths, but that isn't always the case. When it's not going to be the case is when you have a table and you need to kind of check, all right, what are all my partitions here? So here's a function, and I give you certain values inside of it. So the first thing I ask is estimate f prime of 3. All right, well, f prime of 3 is in the middle of 1 and 5. If you want to estimate f prime, I'm going to do f of 5 minus f of 1 over 5 minus 1. That has nothing to do with what we're talking about, but it's a good reminder. So I have 9 minus 5 over 4, which is 1. There you go. There's an estimate for f prime of 3. Estimate the area between the function and the x-axis on the interval from 0 to 20 using LRAM and the 6 intervals given. So my first interval goes from 0 to 1. So my first rectangle has a base of 1 and a height of LRAM, which comes from the left endpoint, which is 4. My next rectangle goes from 1 to 5, which is a width of 4, and a height of 5 because I'm using LRAM. 5 to 9, I've got another width of 4, a height of 9. 9 to 11 is a width of 2 and a height of 12. 11 to 15 is a height of, a base of 3 and a height of 15. And then 15 to 20, I've got 5 times 19. So 4 plus 20 plus 36 plus 24 plus 45 plus 5 times 19. 224. So if I then wanted to use the same idea and do trapezoids, again, I can't just do one big lead coefficient and then a sum. I can do different ones. So I can say, well, my first interval, my first height is technically 1. So h over 2 times b1 plus b2 is 4 plus 5. And then my next height is 4 over 2 times 5 plus 9. And then I have another 4 over 2, 9 plus 12. And then what am I at, 9 to 11? 9 to 11 would be 2 over 2, 12 plus 15. 11 to 15 is 3 over 2, 15 plus 19. And then 5 over 2, 19 plus 20. Whew. All right, let me quick type that in. So I have 0.5 times 9 plus 2 times 14 plus 2 times 21. Where am I? Plus 1 times 27 plus 1.5 times 15 plus 19 is 34. And 2.5 times 39. 250. Well, the good news is they are close, so I don't think I made any calculation mistakes unless I made the same one twice. So there you go. There's your estimate. And basically what I'm getting at here, this one, is just be careful. When you're given a table, don't assume all of your widths, all of your partitions are going to be the same, because they're not. All right, so let's end with a joke. Our joke today is going to be a witch joke. Why couldn't the witches play baseball? Because they forgot their bats. And how do you make a witch itch? You take away the W.